So
All right.
let's get going. Right. So it's my pleasure to introduce Jad Ghalayini, who's going to be talking about a formalization of explicit refinement types in Lean, which I read with great excitement when it came out.
Oh, wow. Great. Hope you weren't too disappointed. So, hi, I'm Jad. I'm going to talk about explicit refinement types. And in fact, I'm going to do something a little more crazy. Hopefully, let's see if I can pull it off. So here's my plan. We're going to speed run the STLC tutorial from the Lean manual, which I'm sure is your favorite part of the Lean manual. Everyone can hear me, right? Okay, and then we're going to sketch syntactic weakening and substitution. And then we're going to sketch semantic weakening and substitution. And it gets worse, because now we're actually going to sketch refinement types. So I said, can I distill this down to something that will fit in a presentation? And it just barely does. And hopefully we'll get to semantic regularity. So you guys can follow along here. We've got some code that's like filled with sorries because I was too lazy to get it to type check, but that's the most important part of Lean, really. So yes. What is a type theory? Okay, let's be quick. Simply typed lambda calculus, everyone's favorite. We got variables. So, here we got a context, which is just, going to be a list of variables, and we have, typing judgment you expect. We got applications, right? Which means we got a function type, and you apply things A to B, you apply it to an A, you get a B. Okay, so far so good. We have lambda abstraction, which says that, if T type checks in gamma X and A to B, then, the lambda abstraction type checks as you'd expect it. And I'm going to throw in some constants. So we're just going to have constant natural numbers because this needs to fit in a presentation. And we're going to throw in a side effect here. This is my favorite side effect. It's called crash. It's commutative, and it does what all my programs do in the end. It's great, right? So now we have a type theory, and my advisor, Neil Krishnaswamy, a very wise man, says the difference between a type theory and a static analysis is substitution. So what are the properties of a type theory? Well, we're going to need weakening, which says that, if this type checks, and I throw in a variable here, then still type checks. And so in other words, if gamma has more variables than delta, and delta says A is of type A, then gamma says A is of type A, cool, right? And of course, we have everyone's favorite substitution, which says that, if this expression type checks with Y of type B, and I'm going to substitute in something of type B, I'm going to substitute in the context, the result should still type check, right? So let's be a little bit more formal here. I'm going to take a function from variables to terms, and I'm going to say it's a substitution from gamma to delta if every variable in delta becomes a term of the appropriate type in gamma. And now this is my substitution lemma that I want to state. If sigma is a substitution from gamma to delta, and delta says that, then gamma says that. So here, that is capture-avoiding substitution, which is going to be the bane of our existence for the rest of our PhD. So yes. Please don't do it wrong, right? How would we represent this in Lean? I'm glad you asked. If only I saw this presentation before starting said PhD. So our types are, well, we got units, nats, functions. That's what we got so far. Don't make me do more than that, please. And that becomes an inductive. Very nice. And we've got our untyped syntax. So we got variables, applications, lambdas, units, constants, and crash, our favorite. And okay, so everything here translates pretty simply, except variables. What do you do about variables? So we want alpha conversion, because we really want alpha conversion, and we need to implement capture-avoiding substitution. There's a typo there, just like in all my implementations of capture-avoiding substitution. That was on purpose, totally, 100%. So what's the solution here? The Brin indices. So we're going to just represent variables as natural numbers, which sounds like a mess, but it's not that bad. So just to make sure everyone's on the same page. In this lambda term, right, we're just going to represent a variable based on how many lambdas we have to hop over to get to it. So here, z, we have to hop over 0 lambdas. For y, we need to hop over 1 lambda. For x, we need to hop over 2 lambdas. And if we have some guy in the context here, we also count variables in the context that we got to hop over. So here it would be 4, since we need to hop over that c there. And so notice now that, going back, constants, right, are just represented as a list of types. Very simple, very nice. And we're less than 5 minutes in. Great. So now that we have our typing context, we can talk about our typing judgment. So we have a type, not a prop. The original ERT was a prop, and I suffered greatly for my arrogance in believing that I could erase this, right? It worked, but lots of casts that, takes in a context, takes in an STLC, takes in a type, and this is a witness, bears witness that the STLC can be typed appropriately. So let's fill it in, okay? So first we've got our variable judgment, and we need to actually write down what does that hypothesis at the top mean in de Bruijn land. So it's pretty simple. It's just, the list contains A at position n. We make it into a type, both to make our life easier, and because later we're going to do this with refinement types, and it's going to be a lot more complicated as usual. Application is translated directly, lambda is translated directly, and everything else is translated directly. Cool, excellent. Formalizing the properties of the STLC. Great. Okay, so now the next thing that we want to do is we want to talk about what weakening means. So we want to define this inductive weakening. It's going to take a function from nats to next, and it's going to take in two contexts. And what's it going to bear witness to? Well, we want to basically talk about its quote-unquote eliminator in big quotation marks. What I want is that if I have that delta has a variable at n, then gamma should have a variable at row n with a compatible type. And so that's essentially the property that we want to be writing down. But again, this is a type, so we can do induction. So this is true, vacuously for the empty list. And if we want to stick another element in the list, then if it's true for gamma, delta, and rho, then it's going to be true for the lift of rho for A gamma, A delta. So what is the lift of rho? It just means that we leave that new variable we stuck at the front alone. Whereas on the other hand, any other variables, they get substituted as usual, but under the suck, right? It kind of sucks, but that's how it is, right? And finally, we've got step. So what does that mean? It means that it's a weakening, so we get to add extra variables on the left, right? And so we can do exactly that. And then the actual function this corresponds to, sucking, right? So great. Okay, weakening. Excellent. Great. And now that we know how to weaken variables, we can check that, this definition is sane by just filling it in. And oh, look, we've weakened variables. Great. Okay. And now we can weaken syntax, and it behaves as you expect. So notice we need to call lift WK on the lambda's binder, because otherwise things will break. Like I said, capture avoiding substitution. And this has all the nice properties you'd expect it to. Weakening by the identity, doesn't do anything, so on and so forth, which is nice because it lets us prove this. This is our weakening lemma written in lean. Exactly, our weakening lemma written in lean, and it's like 10 lines, which is great. Let's do substitution. So our original substitution was, taking variables to STLC terms. That translates pretty directly. And we have our definition for substituting STLC terms is the same. The only weird thing is for lambdas, we again need to lift substitution. So what does that mean? It means leave variable 0 alone. And everything else, we need to weaken it by one step. So what does that mean? It means we just need to shift all the variables up by one. Because, for example, if I substitute, the variable 1 for the variable 0, but now I go under a lambda, then that would actually translate to substituting the variable 2 for the variable 1. Because the variable 0 inside the lambda gets left alone. It's a bit unintuitive, but you get used to it. And now we can take our mathematical definition for substitution and wave the magic leanification wand, which I pray that one day ChatGPT will become. Actually, I guess they tried that, but yeah. Then we have our has_ty.subst, which is basically the substitution theorem. And we could just go ahead and prove that case by case. So for variables, we get to just use the definition. Isn't that nice and clean? For applications, everything is so far so good. But for lambdas, we have this weird s.lift thing. So what does that mean? Well, lambdas say that, that, right? So what does that mean? It means that we need that if sigma is a substitution from gamma to delta, then lift subst of sigma should be a substitution from A gamma to A delta. And thankfully, we can prove that pretty trivially. I'm going to skim over that. And that gives us our proof of substitution. Again, just very few lines. Okay, what is a denotational semantics? Oh boy. All right. So now that we have our type theory, we need to talk about what our type theory means mathematically. So unit means unit, nat means nats. Okay, so far so good. The professor calls this renotational pedantics. Here we have A to B means A to B, really high IQ moments. But wait a second, we have crash. So this actually doesn't work because not every type is inhabited. I mean, okay, in this type theory, yes, but in general, no. So we have to add nothing to Hall. That's a hint for what's coming up next. So yes. And now once we do that, we can give a semantics for context. This is the usual one, But we're actually going to do this. And the reason why we're going to do this is because we want to reason about substituting effectful terms. And of course, for simplicity, we are restricting ourselves to the crash effect, which is honestly what all effectful programs do. That's why we should do pure functional programming. So yes, let us leanify. So we wave the lean wand and wave the lean wand. So the top's a def, bottom's an inductive. They could both be defs, style. No one cares. Right. And now, once we have the semantics for types and contexts, we can have a semantics for terms. So what is it? If gamma says that S is of type A, then we want to take the meaning of gamma and take it to the meaning of A under the appropriate monad. So first, we need to talk about variables, which is a list index, thank God, right? Once we have talked about variables, we can then talk about application. So for the application, we're going to do a bit of denotation. So what are we saying? I'm saying execute S. So I'm taking in my context, which is in the meaning of gamma. I'm going to say execute S. If it didn't crash, execute T. If it didn't crash, then return S of T, which is going to have the appropriate type, namely option B again. Cool. Lambdas always return. They never crash, and they're just going to be the function, which takes in a value and then executes the body in the appropriate extended context. Constants are what you think they are. Cool. Semantic weakening. So now we've got our weakening, right? And we want to convert this to a function from context to context, which is basically just going to drop all the variables we don't use. And we can show this is sane by, just like before, saying that if I have a variable, then taking the unweakened variable and interpreting it in the old context, then interpreting it in the weakened context is the same as taking the weakened variable and interpreting it in the unweakened context. So it's a bit weird, but think about it for a second. And what this basically says is that adding variables doesn't change the meaning of things, which is what you want. And now we can basically prove that that same thing happens with terms. So adding variables does not change the meaning of terms, which is what we want. So great, weakening makes sense. Now we can do semantic substitution. Excellent. So what are we saying? I'm saying that if I give you the meaning of gamma, and I have a substitution from gamma to delta, then you will get the meaning of delta out. And this works exactly as you'd expect it to work. It literally just evaluates everything in the substitution. And again, we check it sane by checking for variables. If I have a variable in delta and I evaluate it in the substituted context, that's the same as first substituting the variable and then evaluating it in the original context, as we'd expect. And then this lets us prove substem. And here's our first sorry of the day, because I'm lazy. But yeah, semantic substitution, which basically says that it's the same thing for terms. So this tells you that substitution does semantically what you expect it to do, which is really nice. So recap, what have we done so far? We sped run the STLC with emphasis on speed run. I realize I've crammed too much into this presentation, but it's too late. We sketched syntactic weakening and substitution. We sketched semantic weakening and substitution. Okay, now we got to do the fun part, which is, of course, refinement types. I'm sure that's what everyone here is waiting for. And we got 10 minutes to do it. So let's see if we get to semantic regularity. What's a refinement type? Okay, so this is nat to nats, everyone's favorite type, right? The seed of uncomputability, right? Aleph. Is this LF1? I don't even freaking know. It's been a long time since undergrad. Cool. Okay, we want to make this a little bit less scary. So we'll instead make it n to n, where b is less than or equal to 10. That's a refinement type. But we also want to support some notion of dependency. So I might, for example, depend on the input and guarantee not only that the output satisfies some property, but that it satisfies some property with respect to the input. Here, that it's also less than the input. So this is the kind of capability we want. The other capability we want is something that a lot of refinement type systems actually don't have, but we get to because we use explicit proof. So, there's always benefits to being primitive, and that's quantifiers. So for example, I might say that I want, given A, I want a number that does not depend on A, such that A plus B is always greater than or equal to A, which is of course isomorphic to just pulling the quantifier into our refinement type. So here I'm highlighting that we can use the quantifier both outside and inside the type. Or, of course, that's just the same as saying that I want a number that's not 0. Now, quantifiers are cool because they let you do cool things like proofs, all within your refinement type system. So here we have addition is commutative, some really advanced mathematics. I'm sure everyone here is very impressed with that. And of course, we have our favorite thing, which is accessing the length of a list. So accessing the length of a list, it sounds like nonsense, but assume a list is actually stored as a linked list in memory, you actually need to compute it. So we're making a distinction between the mathematical value, which might be non-computable, and the actual computed value. And what this is basically saying is that this is going to calculate a value that is equal to the appropriate mathematical value. So what would a term like this look like? Well, we have a magic lambda that binds the ghost, and then we take our set, we destructure it, and we apply the appropriate calculation. The cool thing about this is that we can erase it. So namely, what's going to happen is our magic lambda is then just going to become a unit binder. We need the unit there for reasons of consistency, right? And then on the other hand, all the proofs basically disappear. And then we end up with, the unit binder on len by eta. So that's really nice. What we can do is we can just erase things to kind of forget about all the refinement information. And this kind of segues into the semantics of refinement types. But before we talk about that, we need to talk about one little detail, is that we have dependent quote-unquote types, which means types are allowed to depend on values, which means we need a judgment that says that a type is valid. And that also introduces the problem of determining whether a context is valid, because we need a context to be valid based on the types inside it. So that's pretty straightforward. And once we do that, we have this little technical lemma called regularity, which just says that if A is of type A, then A is a valid type. So that's important. So once we keep this in mind, we can talk about the semantics of refinement types. So here's the naive semantics of refinement types, is that the A is just going to be a subset of the thing. And that works perfectly fine if we didn't have dependency. Unfortunately, we do have dependency, so it needs to be a bit nastier. So what is this saying? It's saying that we're going to take the erasure of the context, and we are going to give you a subset of the type depending on what values are in the context. This also gives us a semantics for a context being valid. It's just going to be a set of valid contexts. And then we can just define what that is recursively pretty simply. And now the big theorem, semantic regularity. This means a refinement type system is consistent, that it makes sense, all the good stuff. What does it say? It says that if gamma is of type A, and I have G, which lies in the meaning of gamma, and moreover, G, which is valid by our refinement type system, then if I take the erasure of A, which of course we're guaranteeing is well typed, and evaluate it in G, that is going to lie in the denotation of the type A. So in other words, what it's saying is that if everything in my environment is in the set that my refinement type system says it's in, then my output is also in the set that my refinement type system says it is. And this tells me my refinement type system is consistent. The reason why it tells me my refinement type system is consistent is because false is the empty set. And because false is the empty set, that means that if we had a proof of false, we'd have an element of the empty set, and therefore we could get a contradiction in Lean. So any mistake in our refinement type system also means Lean is wrong, which is nice. So how do we represent this in Lean? Okay, now we've really got a speed run. So I'm going to skim over a lot. Well, terms, these are our familiar terms from before, but we're going to add two things. So this is a very bare bones refinement type system. ERT is much more complicated, but I'm just skimming the ideas. We're going to add a little flag here that's going to tell us whether the variable we're binding is a ghost. So whether it's the magic ghost lambda or the regular lambda. And we're going to add in a proof. We're going to add in a proof for everyone's favorite proposition, that A is equal to A, reflexivity. And now since we have dependent types, we need to add types to our ENA. So specifically, we're going to have a pi type that's going to go from A to B. And it's also going to take in a flag that's going to say whether A is bound as a ghost, in which case we're going to write it as for all, or we're just going to write it as a regular arrow otherwise. So notice, actually, it's false if A is bound as a ghost, which is a bit weird, but that's how I wrote it. And then we have unit nat, and finally EQ. So EQ is the type of witnesses. Here we're just treating it as a type rather than a prop, which is fine because we have ghosts. So we could just say it's a ghost type and it will computationally erase, just as if it was a prop. So it's the type of witnesses that S is equal to T, where S and T are both members of A. Okay, cool. So we've got that, and we can define type erasure, which is just going to take terms to types. So notice invalid types will still just, everything will just map to unit, but that's fine. And similarly, we can erase things to STLC. And again, I've just sent invalid things to nil. It doesn't actually matter what you send invalid things to. Once we have our erasure, weakening works exactly the same, except that types weaken just like terms. And substitution works exactly the same, except that types substitute just like terms, which is nice because it saves us some time. Now, contexts are the same, except that we have to carry around a Boolean telling us whether a variable is a ghost variable or not. And now once we have a context, we can talk about erasing it. So computational variables stick around, ghost variables get sent to unit. Then we also have the upgraded erasure, where everything sticks around. This is important because it lets us talk about regularity. Moving on, we have a downgrade function, which is basically just going to take the upgraded context and send it to the regular context by just forgetting things that need to be forgotten, right? And now, finally, we have our typing judgments. So we can't stick ty there because term can have a dependent type. Term works, but we also want to talk about whether types are valid or not, and we want to distinguish ghost and computational ones. So we just introduce a new inductive that basically says either something is a type or it's a term, and we'll say whether it's a ghost term or a computational term. So let's go ahead and do that, and we will just say, pi, eq, they're both what you'd expect them to be. Unit and nat are what you'd expect them to be. And then we have our valid context judgment from before. And now that we've done that, we can have our first kind of really complicated thing, is variables. So variables here, we're going to say that a computational variable can be interpreted as a ghost. That's what the k greater than or equal to thing, but not vice versa. So ghosts cannot become computational. That's the first thing. The second thing, which is really annoying, is that we actually need to step the type of our variable. And the reason is because, assume we have something that uses index 0 at, the head of our list. Well, that's not valid anymore, especially if we have 0 of that type. So we need to step it so it uses index 1. And similarly, every time we add a new variable, we need to step again. So that's why we needed this inductive var judgment before to make analogies here to, let us do the stepping. So we did that. And just to check that everything is sane, we show that, any computational variable can become a ghost, but not vice versa. Great. Now, lambdas are what you'd expect. Applications are a little bit weird because we need to substitute by t.sub0. So what does this mean? It means that for every instance of the bound variable in there, we replace it with s, and everything else just gets decremented by 1. So that's sub0. Cool. Constants are exactly what you'd expect, and proofs of reflexivity are what you'd expect. And we check that any computational term can become a ghost term, but not vice versa. Okay, and erasure basically says that every term is well typed in the upgraded context, whereas computational terms, but again, not necessarily ghost terms, are well typed in the regular context. Okay, then we have some little theorems that we don't care about. And weakening and substitution work roughly the same way. There are some complexities, but we don't have times to do it, because we want to talk about the semantics of refinement type, which thankfully we can just literally translate our mathematical signatures quite straightforward. So again, the denotation of a type is just, I'm going to take the upgraded context. I'm going to take the upgraded context, and I'm going to return a subset of the denotation of the erase type. And the denotation of a valid context is just a subset of the upgraded context. And finally, we can state the big theorem, semantic regularity. So what does this say? Let me read it out for you. For every valid context gamma, right, if I have some term s, which in gamma is of type A and kind k, where k tells you whether it's a ghost or not, right? If G is a valid environment, then there exists some A, so that first off, H erased, interpreted in G, terminates and gives you back A, and furthermore that A lies in the subset that you can get by applying regularity to H. So that's nice. And then finally, the last thing that we want is we want to say that ghosts don't matter. And that's simply irrelevance. So what is that saying? It's saying that if I interpret a type, if I interpret the upgraded erasure of a type in the appropriate environment, that's the same as interpreting the regular erasure of a type in the downgraded environment. So notice if we go back to our downgrade function here, where's the downgrade function? I've skipped it. Okay, I can't find the downgrade function, but the downgrade function sends things to null. So that guarantees that these values will never be used, which is nice. And basically, what is explicit refinement types? It's doing exactly this, but at a much more complicated scale with existential quantifiers and whatever it is. And I thought that was the best way to explain it, is to try to jam it in 25 minutes. Let me know how well that went. Questions? I'm sure there's a lot of them.
You hit the timing perfectly. It's 54 past.
I will say I greatly enjoyed the style. It was very fun.
Thanks.
Yeah. So, please raise your hand if you have questions. No questions. All right. I actually have something. So in the paper, you give what feels a little bit like a lukewarm endorsement of lean, sort of saying like, we tried it and it worked, and that was a pleasant surprise. Is how I kind of remember the particular paragraph. Um, has but this was also some time ago, right? Like maybe a year or two.
Yes, yes. So I am a much more enthusiastic like lead user right now. So I'll tell you what happened, right? Because my professor finds it very funny. So I have this thing about using bleeding edge software, and I didn't want to use Coq because I didn't like the syntax. So I told the prof I want to use Lean, and he said use Lean 3. I'm like, I want to use Lean 4. He's like, why? I'm like, I just want to. So at this point there was no mathlib. So I had to write my own nat lemmas. I had to write some of my own tactics. I had no idea what I was doing. I had never used Lean before, but I felt like it because I was just so tired of Coq. I thought I want to do something new, you know? And yeah, so we reported multiple bugs because Lean would regularly like crash on our definitions. We're actually, we ended up complaining enough to get the desymp tactic introduced because the simplifier would hang on a 50 case induction. We had to deal with all kinds of things, but in the end it was very pleasant because like the lean developers would just immediately kind of respond to things. But I'm going to be honest, like it was not the most practical choice at the time. And that's why now I've actually come back to it because I'm doing some more work on higher order logic and refinement types. That was the whole adding nothing to Hull thing. And I've been rewriting things and stuff. And I found everything is much more pleasant to use. I just pull in mathlib as a dependency. I don't need to bleed from my eyes anymore. And yeah, I'm having a much better time now. And also I learned some lessons, like for God's sake, please don't try to make everything a prop for efficiency. It's not going to be efficient either way. And you're going to go to cast hell if you do that. So yeah.
I think it no longer makes my eyes bleed is the most amazing endorsement I've ever seen for a piece of software.
It's amazing. It's great. 10 out of 10.
Do we have any other questions? Really? Do I just get to stand here and ask questions all the time? This is awesome.
Okay.
Cool. So another one is why are you confident that your de Bruijn index munging is actually the correct thing? Because that strikes me as being sort of definitional rather than like the thing that you prove correct.
Yes. So the de Bruijn index munging is correct, I think, because the semantics are correct. So the semantics are very simple, right? They're just, a variable is interpreted as indexing into the list, right? And a context is interpreted as, a vector, right? So I know my de Bruijn index munging is correct because when I go and I take the term and I put it into the context, it does exactly what you'd expect it to do. So, and now you might say that this is a bit of a roundabout way to go about it, but what happens is that, you make mistakes with this kind of thing, and the semantics breaks until you don't. So, yeah.
That makes sense. What? Thanks. I think we have time for one final question if anybody's gathered the courage after this fire hose of information. All right. Thank you very much. We have one question from Freek Wiedik.
Okay, so my question is, these refinement types are a type system, and you use Lean basically for the semantics in some sense and for the meta theory. Can you also translate them into Lean terms? So basically consider it as some kind of subsystem of the Lean type system. Does that make sense? Because the Lean type system is very rich, and these refinement types are very practical, so not very rich. Is that something you can do?
So theoretically, probably. So one of the advantages of the refinement type system is that you could do erasure, and any translation into Lean would probably lose that erasure advantage. So probably what I would do is if I were to like try to integrate this with Lean, I'd say the more natural way would not be to translate to Lean terms, but rather to use the semantics, right? Because the the semantics can be non-trivial. So the semantics could be, for example, a proof of some proposition P, and then that proposition is going to be equal to the appropriate lean proposition, because lean has propositional extensionality. So that's probably what I would use the terms for, is to do things like proof propositions rather than just like embed them straight into lean. But yes, you could probably do that. I haven't explored it that much.
Okay,
Does that-
thank you.
So once again, thank you very much. Could you please stop sharing your screen so that Joe can get